Hi everybody and welcome to another video in the Deep Learning for Audio with Python series. This time we're going to talk about recurrent neural networks and understand the theory behind it. So let's get started and understand what RNNs are, what they do, what type of data they process. Now, there's a lot of data in which order is extremely important. That's true, for example, like for text and words. So let's analyze, for example, the sentence, Anna loves John. Well, here, order is very important because Anna loves John is very different from John loves Anna, right? And the point being that order is so important that many bad things can happen, like if you don't understand whether Anna loves you or John loves Anna, right? Okay, so in that sense, order is very important for data, certain type of data, like time series as well, where we have data which are measures of different values that are taken a certain interval and ordered over time, right? So this is a type of data that's very important, and we want a network that can understand and process that data and maintain and understand the order there, right? So another point is that usually, say for example, we have a time series or even just a sentence or a piece of music with a melody. So it turns out that melodies or sentences can have a variable number of words or notes, right? And so we want a network that's able to process data, sequential data, regardless of the number of words or notes or data points that we have in there. So RNNs, in a sense, try to address all of these issues. They're used for sequential data. The great thing about them is that they process data in such a way that each data point is processed in context. So we look back at what happened before to understand what to do next, with our data and how to predict. So obviously, audio and specifically music are kind of so the type of data that we have for audio and music resonates very well with RNNs, because we can think of audio as a time series itself. So a series of points taken at certain intervals in time. So if we think of a waveform, for example, we can think of it as a univariate time series. So what does univariate mean? Well, it means that we have only one value, one measure that's taken at each interval. So now let's take a look at the at the data shape that we have with a waveform expressed as a time series. So here we have it. So the first dimension is basically given by the number of samples or number of intervals where we are taking measures. And this is given by the sample rate, which in this case here is 22,050 by 9, which is the number of seconds, right? So here we have more or less 200,000 data points in the time series. And then here we have, as the second dimension, 1. And that's because we have only one dimension, which is the amplitude that we are taking at each data point. Right. Now, let's take a look at another type of data that we've used quite a lot, in our the last few videos. And that's the MFCCs. And we can think of MFCCs as a multivariate time series. Now, first of all, if you don't remember what MFCCs are, just take a look at the video below here, and you can understand what MFCCs are and why they are super important for audio analysis. Cool. So now let's go back to the interpreting MFCCs as a multivariate time series. Here we have values at different intervals, and then for each value, for each interval, we have 13, in this case, values, and each of the values represents a coefficient. It's an MFCC, right? And in this case, we're talking about a multivariate time series because we're taking more measurements for each interval. And the relative dimension here is given by the overall number of intervals. And in this case, we have the sample rate divided by the hop length, which in this case is 512, which is like quite customary. Again, if you don't remember, just go back and watch like my previous video on this. And then we multiply that by 9, which is the number of seconds. So overall, we have around like 387 intervals. And then the second dimension is given by the number of MFCCs, which is 13. So in other words, here we have 387 intervals. At each interval, we have 13 values. Right. So this is the type of data that we can use with RNN. So this kind of like time series where we have a number of like values for at different like intervals. Right. Okay, so let's take a look at how RNNs work, like from a very, very high level perspective. So first of all, the idea here is that we have like this time series type of data and we feed it into the network a point at a time. So we give it like a data point, a step like every time. And the idea is that the network is going to be able to predict the next step given the step we are currently giving it and the history there, right? So the prediction depends also on the context, on what happened before. Right. So this is like a very, very high level intuition of what an RNN is. So now let's take a look at, let's like dive down into an RNN architecture. So here we have our inputs, which is like given by X. Then we have a recurrent layer, which is obviously like the focus of an RNN. And a recurrent layer is a layer that's able to process sequential data in a sequential way. And we'll see what this means in a second. Then the output of the recurrent layer usually is fed into a dense layer, which does some classification using softmax, for example. And then we have the output, which is Y. Right. Okay, so now a thing that I want to try like to look into here is the dimensionality of the input. So the shape of X. So in this case, we have a 3-dimensional input. So the first dimension is the batch size. So it's the number of samples of time windows that we are passing into the network at once. Then the second dimension is given by the number of steps that we have in the sequence. And the third dimension is the number of dimensions, the number of different measures that we have in the sequence itself. So for example, in the case of a waveform, which is a univariate time series, this third dimension here would be equal to 1. In the case of the MFCCs with 13 coefficients, we would have 13 here. And that's a multivariate time series. Remember that. Okay, so this is more or less the architecture from a very high level point of view. Now let's get into the recurrent layer and understand how it works. Cool. Okay, so for the recurrent layer, the most important component is the cell. The cell, it's the one that kind of like processes all the information. And here we can have a lot of like different types of cells. So for example, here, like with a simple RNN, that's what we are analyzing like in this video. We're gonna look at a very simple, like dense layer with a hyperbolic tangent as the activation function. But then we can have also other types of cells like a LSTM, long short-term memory cell, or a gated recurrent unit. We're gonna look into this like in the next video and understand why they are important. But then again, the cell is the one that's responsible for processing this sequential data. Now, at each step, we kind of give in a input data that's represented by this xt. Then the cell does some processing and it outputs a couple of things. So it outputs h of t, and ht is basically, we can call it a state vector or a hidden state, right? And this represents and keeps memory like of the cell, of the network, like at a certain point in time. And then we also output a yt, which is the actual output. And here the whole point of the recurrence here is given by the fact that the ht, or the state vector, is going to be reused at a later point, at the next step, and so that we can have like information about the context. So basically the whole idea here is that we are giving information sequentially, step by step, to the cell here, and then we output both an output and a hidden state, and the hidden state or state vector is going to be reused for the next step. Now, the whole point is that we have like recursiveness here, because we are just like feeding back some information into like the cell from a previous computation. So let's try to unroll this process into like a linear way. Okay, so now let's imagine we have a sequence with n different steps. So we'll start from the first step here. So we'll pass in x0. x0 gets analyzed and processed from the cell, and we get an output which is h0, which is the state vector at this time step 0, and then we have the output which is y0. Now, the next step is sending in x1 as a data point, and x1 is going to be used in conjunction with h0 to output h1, which is the new state vector, and at the same time the cell will also output y1, right? Okay, so we continue and we pass in x2, we consider h1, and we output h2 and y2. We can continue this like for as many steps as we have until we get to the end. So in this case, it's the nth step. And so here it's the same thing that we've done so far. So we input xn, we consider the state of the cell at the previous step, so at n-1, and we combine those two information, and we get a new state vector here, hn, and we get an output called yn. Now, the thing that's really important to understand here is that each of these time steps, so at each of these time steps, we always use the very same cell. So we just have one cell, but we use it recursively. And so from this, the whole point of calling this network a recurrent, right? Because we are recursively using the very same cell time and again to output to process new information in a sequential way. Cool. So now what I want to do is take a look at the dimensionality of the data that flows through an RNN. So let's take it as an example, an input where we have this dimensionality here. So we have a batch size is equal to 2, 9 steps in the sequence, so a sequence with 9 items, and then we have a univariate time series here. So we only have one value, one measure per step. Okay, so here we have our RNN, basically our recurrent layer unrolled. And as you can notice here, we have 9 steps. Obviously, it's 9 because it's the number of steps that we have in the sequence. Okay, so for the input at each step, we have a dimensionality that's equal to the batch size and the number of dimensions. So in this case, each data point is equal, it's not equal, but it has a dimensionality of 2, 1, right? Okay, so let's take a look at the output here. At each step, we have a dimensionality that's equal to the batch size and the number of units. So we are basically outputting as many outputs as the number of like as the batch size, right? Okay, so in this case we have 2, 3, right? And here we are saying basically that we have 3 units for the recurrent layer. Okay, so if we consider the whole output, so y0 up until y9 all together, the output shape is 3-dimensional, right? And so here we have the batch size as the first dimension, the number of steps as the second dimension, and the number of units as the third dimension. And in this case, we have 2, 9, 3. Cool. So now what remains to do is look at the hidden state, or the state vector. And it turns out that in simple RNNs, the state vector is equal to the outputs, right? So for example here, this h0 is equal to y0, and obviously the dimensionality is the same. So we have like 2, 3. That's good. Okay, so now let's take a look at a couple of I would say like flavors of RNNs. So we have one that's called sequence to vector RNN. And here the idea is that we input a sequence, but the output that we get is only like a single vector here. So basically here we are just waiting for this y9 value in a 9-step sequence, and we drop all of the other predictions before, so y0, y1, y2, we drop all of them, and we are only focused in the last bit that gets predicted. And this is like quite usual. So for example, if you use an RNN for generating a melody, so what you can do basically is you provide an input, and this is a sequence, a melody, right? So we have like a sequence of notes, and there you are interested in the next notes, but you're not necessarily interested into like the previous notes, right? Okay, so this is a sequence to vector RNN, and it's opposed to a sequence to sequence RNN. Here we consider like as an output all the outputs at each time step. And so basically here the idea is that we input a batch of sequences, and then we get as an output a batch of sequences again. Right, so this is a little bit less common, I would say, than a sequence to vector. And this is reflected also like in how Keras works. And indeed the default behavior for simple RNN layers is that of having a sequence to vector network instead of sequence to sequence. Okay, so now we've spoken so far about the architecture of a network, of a recurrent neural network, but we haven't really dug into a memory cell that much. So for simple RNNs, the memory cell is a very simple neural network. The idea here is that we use a dense layer, and the input is given by the combination of the state vector and the input data. So the state vector at the previous time step, and the input data obviously at the current time step. And the activation function that we use is the hyperbolic tangent, or tanh. Now you may be wondering, but why are we using tanh? Haven't we always used like other types of activation function? Right, but it turns out that training an RNN is quite difficult because of a number of reasons, but mainly we have like vanishing gradients, so the gradients tend to disappear, and we'll understand why that's the case in a while. And at the same time, we could have the issue of exploding gradients, so gradients that are growing bigger and bigger. And the problem is that if we use ReLU, which we know like works really, really well with CNNs, ReLU is not bounded, and so ReLU can explode. Whereas tanh constrains the values between -1 and 1. So by using tanh, we're avoiding the issue of exploding gradients. But now let's understand how we train a network. And so to train a recurrent neural network, we use a variant of backpropagation, which is called backpropagation through time. So basically here, the idea is that the error is backpropagated through time. So what we usually do here is that we take the RNN, we unroll it, and we consider each time step as a layer in a feed-forward network. Now, I guess like you start seeing the problem here, which is basically, so say for example, we have an input where we have a sequence with 100 time steps, right? And there, that basically means that when we unroll the RNN, we have 100 layers. Now, this is a very deep network, and we know that when we have a very deep network, we have the issue of vanishing gradients. And so basically what we do at that point is we calculate, we calculate the error, then we propagate back the error through all these virtual layers, which are like all the different time steps here. And so while we go all the way back to like the early layers, we have an issue with vanishing gradients, right? So these gradients can disappear, they can explode. Okay, so there's a nice way to like avoid some of these issues from happening. And basically what we do here is we use a sequence to sequence approach. So here, while we train the network, we output predictions at each time step, and then we compare them against the targets. And obviously we expect for the targets to be the inputs, but shifted towards the right by one step. And so with that in mind, so we can say, for example, that the target here, like at time 0 is x1, and at time 1, when we input x1, we expect x2, right? So at each time step, we calculate the error and we backpropagate the error. And by doing so, we kind of like stabilize the training process, because now we are calculating like gradients, like also like locally. And so if we have like a big error at a specific time step, we can just like propagate the error like there and tweak like the weights like on like the layer which has like the most problems there. And by doing so, basically we speed up the training process and we make it more stable. But now this is only like a trick, because in the end, once we've trained the network, what we can do is just magically drop all of the different points here. So you drop all of the sequence to sequence predictions and just focus on the last prediction, which is the one that we usually want when we use a sequence to vector RNN. Cool. So this is backpropagation through time. Now, let's take a look at a little bit like at the math behind an RNN and how it works. So for understanding that, we should just like focus on one time step. So here we'll focus on xt, right? And so here we have the input at time t, we have h with t minus 1, which is basically the state vector at t minus 1. Then we have ht, which is the state vector at time t, and yt, which is the output. Now here, I also have in red u, w, and v, and these are weight matrices, and we're going to use them for calculating the state vector and the output. So u is connected with the inputs, w is connected with the state vector, and v is kind of connected with the dense layer, and it enables us to get to the output. Okay, so let's calculate first of all ht, which is the state vector at the current time step, right, at t. Okay, so for doing this, we have like a function, the activation function, which in a simple RNN is just like tanh. And so we have this function that depends on a couple of things. It depends on xt, which is the current input, and it depends on the previous state, right? So this is very intuitive because the current state depends on the input data for that state, for that time step, and the state vector for the previous time step. So that is like the context, right? So now that we have a ht, we can get the output, and the output is just a softmax activation function applied to ht, right? And here we have obviously like a multiplication between V, the weight matrix, and ht, and that gets into basically the dense layer, right? So now the question is, but what do we learn when we are training a recurrent neural network? Well, we actually learn these two functions, and more specifically, what we learn are these weight matrices, so U, W, and V. Nice. Okay, so recurrent neural networks are really, really good up to a certain point though. And the problem is that they really don't have that much of a long-term memory, which basically means that they can't be used like to see that much like into the past, which so the problem with this is that they can't learn patterns with long dependencies. And we know that a lot of like this time series type of data, audio data, music data has like long-term dependencies. So think, for example, of a song. So there you have certain musical structures like a chorus and a verse, and a verse that's like, I don't know, like a verse that's used like at time, I don't know, like after 2 minutes in a song. Well, it kind of depends to the very same verse that was used like at the beginning of the song, but with an RNN, we can't really remember those long-term patterns, right? And this is a bit of a problem, because that basically means that the RNN isn't capable of understanding like these patterns and making prediction that keep track of the context. So in order to avoid that and tackle this issue, a number of different types of RNNs have been devised, and a specific one that's very successful, it's called long short-term memory network, or LSTM, and this is going to be the focus of my next video. So I hope you enjoyed this video. If that's the case, leave a like, and if you have any questions, because I know like this was a little bit like of a tough topic like to understand, please ask those questions in the comment section below. And if you want to like have more videos like this, remember to subscribe and activate the notification bell, and I'll see you next time. Cheers.